Let's start on this core idea called VSEPR theory. Okay, perhaps maybe it's important for me to tell you guys, right? What are the core ideas in Chem bonding? Okay, last lesson we discussed structure and bonding. That's the first core idea. Today we'll be moving on to the second core idea called VSEPR theory. And for that, right, you kind of need to know how to draw your dot and cross diagrams. Okay, I taught you guys a little bit before that. So for today, right, okay, we're just going to practice a bit more. Going to recap dot and cross. And then I will touch on other stuff today as well. Okay, but mainly today is on VSEPR. Okay, the following lesson I'll touch on the third core idea. Okay, but for today we're going to explain some other stuff as well. Okay, I'll touch a little bit more on electronegativity, and I'll also talk a bit more about this thing called intermediate bonding. Okay, so today that's the agenda, right? So 3 things for us to discuss. Okay, the part of the lesson will once again just be on VSEPR theory. Okay, so let's do a quick recap of what we have done for dot and cross diagrams before this. Okay, so some of the core ideas are such. Number 1, right? Okay, we discussed the idea of valence electrons. Okay, you need to have 8 valence, but as we have already seen, there are situations in which you can hold less than 8 valence, or even cases that can hold more than 8 valence. So in other words, right? Okay, we're gonna explain this part today because I haven't taught you guys how how some elements can hold more than 8 valence yet. So we'll touch on that later on. Okay, but then also we discussed the idea of central atoms. Okay, central atoms are usually the atoms that can form the most bonds or the less electronegative atom. Now remember, for electronegativity, you all just need to remember the top 3 most electronegative elements. Can you remember what it is? Who are the top 3 most electronegative? FON, right? Okay, good. Okay, so FON, F being number 1, okay, on the in the periodic table, then 2, then 3. Okay, today we'll touch on a little bit more on electronegativity as well. Okay, I'm not going to go over the rules all over again now because I just do this for recap. So anyways, okay, right after central atom, we also discussed, right, on the side atoms. Side atoms is important to know how many valence electrons they have, right? Because it corresponds to the number of bonds that they can form as well. Okay, so this one is just number of valence electrons. Will tell you how many bonds the side atoms can form, and it will save you a lot of time. Okay, then afterwards, I also told you guys, after you fill out the side atom, you must check back at the central atom, right? And then there are 2 scenarios. The first scenario is this. If the central atom can hold more than 8 valence electrons, then what do? Do you need to change it to anything else? No. Okay, so take note. If central atom can hold more than 8, you leave your answer. Okay? That's right. Okay, but okay, we're just doing a recap of dot cross stuff. Okay, but anyways, if the central atom cannot hold more than 8, then what do we do, guys? Can you remember? Okay, if you cannot hold more than 8 valence electrons, then you need to include what kind of bond? Can you remember? Okay, good, the dative bond. Okay, so dative bond, I already mentioned before, is the last resort. Okay, so it's been a while since we talked about this, so let's just do a quick recap. It is the last resort, meaning to say, right, if you can expand the octet, if you can hold more than 8, that's your answer. If cannot, then you change to a dative bond. You shouldn't be going into a dot and cross diagram, okay, expecting to draw a dative bond. Okay, it should be the last thing that you think of. Okay, and also, I told you guys most of the time, whenever this situation comes about, right, your dative bond is always given from the center to the side. Okay, central atom given to the side atom, and that is the rule for dative bonding. Okay, so far so good. Okay, so generally those are the basic rules. Now I'm going to dive into the different types of species that we have covered so far. Okay, so then later, right, we'll just try like 4 dot and cross diagrams. Then I need to move on to VSEPR. If not, we won't have time. Okay, but anyways, okay, the first type of species we talked about were ions. Now, ions are very simple because we learned this in secondary school. Okay, ions got positive and got negative, right? Then how do we be doing this? Okay, what should we talk about? Okay, so remember, I'm pretty sure you guys still know that plus charge means you remove an electron. Okay, minus charge means you add an electron. Okay, but the issue is, who do you remove an electron from? Can you remember? You remove an electron from the more or less electronegative atom. Okay, the less. Okay, because In this case, right, you want to remove from the less electronegative atom is easier. Okay, but when you add an electron, right, you add to the more electronegative atom. So the idea is that a strong person versus a weak person, if you give an electron out, right, the strong person will probably take it first. Okay, so you give it to the more electronegative. We look at a few examples today, right, and then we'll just move on to the other concepts really. Okay, but I also talked about radicals. Can you remember what a radical is? Okay, remember the one with only one electron? Okay, so recap. A radical is a species containing an unpaired electron. Okay, not any species can have this. It's only if there are an odd number of valence electrons. A very, very common example would be, okay, let's just write some examples down. NO2 and NO. We have actually drawn NO2 in the first time I saw you guys. Okay, so this one we actually drawn before. Okay. So in these cases, because nitrogen has an odd number of valence, we can actually put a lone electron on nitrogen like this. Okay, so sometimes radical you just see a random dot on the structure. Okay, so we have no longer drawn this really. Okay, today I'm going to look into the last example. So I think it's like page 21 or something, I'm not very sure. Okay, page 24, sorry. Okay, page 24 of your books. Okay, we've covered all the way until here so far. Okay, we also talk about some special cases. For example, N2O. N2O is a very good structure to showcase the rules of the central atom. Okay, I'm pretty sure we've covered all of this already. Okay, but today, guys, I'm going to explain why some elements can expand their octet, basically hold more than 8 valence electrons. Okay, why is that possible? It's because, first of all, you'll be asking who? Who can expand the octet? Must know that. Period 3 elements and below. Now, what does below mean? Below literally means below. Like you see the periodic table, like physically below. Below period 3 is period 4, 5, 6, 7. You can tell that the majority of the periodic table can actually hold more than 8 valence. In fact, a minority, only period 1 and 2, can only hold a maximum of 8. So a rather interesting observation. Okay, you will notice that actually most people can hold more than 8. So the octet rule is kind of weird. It's not that good of a rule as well. Okay. Then the next question you will ask is why? Why are they able to expand the octet? Why period 3 and below? I just need you to copy down this explanation. Every time they ask you why, right, you just need to write these words. They have energetically accessible vacant 3D orbitals. Okay, so that's why the first part of the atomic structure will come in. Over here, we need to know what orbitals are, which I'm sure you guys know already. Okay, and then we need to understand how expansion of octet works. Okay, highlight 2 keywords. Energetically accessible is one phrase, and then the next most important one is the word vacant. Okay, first. So now I'll just show you guys some examples. I'll teach you how they can actually expand their octet. Okay, usually you know this is enough already, but then I don't think that's. Okay, I think we need to go in. Okay, so let's see. All right. I will draw a period 2 element, and then right below it is this period 3 element, nitrogen and phosphorus. Okay, let's write the electronic configuration. So very quickly, guys, go and write down the electronic configuration of these 2 elements. Okay, remember, I'm not the 2.8 one. Okay, it's the 1s2, so on and so forth. Okay. It shouldn't be a huge problem here. So this, and this. Okay, should be all good. Okay, phosphorus, just do the same thing, but now because it's in period 3, right? You can go all the way until the 3rd quantum shell. Okay, so that's all we have here. Any issues with this? Yeah. Now, guys, when we look at bonding, right, dot and cross, are we looking at all the electrons or just the valence? Just the valence, right? So I just need you all to highlight all the valence electrons. Can you all tell me where are the valence electrons here? Nitrogen, where are the valence? Is it just 2p3? No, valence shell is referring to the valence quantum shell. So it's the entire second shell, basically. Can you see that? And then for phosphorus, because it is one period below, right? It is in the third quantum shell. The third quantum shell is the valence shell. I'm only going to focus on these shells. Okay, then I'm going to draw this thing called the electron in box diagram. Can you remember what that is? Okay, can you remember what the box represents? Okay, electron in box. Okay, what is, okay, the electron is always in the what? Orbital, right? Okay, good. So don't tell me subshell, don't tell me quantum shell. A box represents an orbital. And recap from atomic structure, one orbital can hold how many electrons? 2. Okay, so over here, let's draw 2s2 and 2p3. 2s, we have one box, right? So 2s2 like this. As for the p subshell, how many boxes do I need to draw? 3. One p subshell has 3 orbitals. Draw 3 like this. How do we arrange the 3 electrons? Do we just put 1, 2, then 3? They should always be single first before you pair them up, right? Okay, so something like this. Okay, now we do the same thing, right? For 3s2 and 3. They have the same exact subshells, so same number of orbitals. So something like this. However, I'm going to recap a bit of atomic structure with you guys. Okay, if you all remember, we have a hierarchy. Quantum shell followed by, what's next? Subshell followed by orbital. Okay, guys, this is the hierarchy. Now let's go into more detail. Quantum shell, we use what to denote? The alphabet or the number? Okay, number, not like alphabet. Okay, so the number, quantum shell, we got 1, 2, 3, right? And okay, let's just stop here for now. Okay, guys. The first quantum shell has how many subshells? I mean, you can just follow that one. The first quantum shell only has the S subshell, right? So first quantum shell only has S. Second quantum shell has what? Is it just P? S and P. So the first shell has S. Second shell has S and P. Third shell has 3 only, right? S, P, and P. Okay, that's not really the issue here. Okay, what I want to talk about is mostly the orbitals. You all can go and split it all that. Okay, and S subshell has how many orbitals? 1, P has 3, D has 5. Okay, so you can see the splitting like that. Okay. So guys, ask same thing again. The second quantum shell only has S and P, correct? But the third quantum shell has S, P, and D. Guys, only the S and the P are occupied, right? Is the D occupied? No. So what we're going to draw over here, right, is an additional D subshell with 5 boxes. Again, because we just mentioned 5. Oops. Okay. Now, as we can see, there is no electron needed to fulfill the 3p subshell because it goes until 3p and that's it. But guys, I want you all to know this. It is still there. It's just not used. Okay, it is still there. It's not that it doesn't exist. Okay, just because there are no electrons inside doesn't mean it doesn't exist. Because the third shell has deep subshell inside. Okay, it's just not using for anything. Can first? Okay, okay. Does 2 have a 2D? Is there such thing as a 2D subshell? No, right? Okay, so we don't draw anything here. Okay, now come. Let me show you all an analogy. Hey guys, anyone live with their anyone have to share rooms with their siblings? Okay, probably have, right? Okay, do you all like it? Say real. No, I also don't like it. I'm 23 years old, I don't have a room. Yeah, I don't have a room to myself, and I do not like it. But if you don't like it, what will you do? You will move to another room only if you have an extra room, right? Okay, but my house too small. Okay, so guys, I'm basically nitrogen. Can you all see, electrons don't like to be with each other, right? So, but can he move out? Is there any other room extra? No, don't have. So too bad lah. But as for P, imagine if you live in a bungalow. If I live in a bungalow, right? Do you really think I'm gonna live with my brother? Okay, no. I would move out the second I can, right? And guys, can I do so in this case? Why? Why can I do so? Because I have 5 extra rooms not being used, right? So what I will do over here is this. Electrons are the same, they don't want to stay with their friends. Okay, so they will come here and the electron will just live by himself. He has extra rooms in his house, he can do this. Nitrogen doesn't have extra rooms. So guys, I ask you all, over here, can I ask you how many unpaired electrons there are in nitrogen? How many unpaired electrons? 3. Guys, if you have 3 unpaired electrons, how many bonds can you form? Each bond wants to form 1, 1, 1, right? So you can form a total of 3 bonds. That's why nitrogen can form 3 bonds. Okay, the previous way that I explained was over here. The side atom nitrogen has 5 valence, so you all tell me 3 bonds. But actually, there's another way you can explain this. Okay, it's the fact that you have 3 unpaired electrons. Make sense? So guys, you take a look. If you have 3 bonds, right, what's the maximum? Actually, never mind. We come here. Okay, guys, you look at this situation now. How many unpaired electrons are there now? Phosphorus can go up to 5 unpaired electrons, right? Which is how many bonds? 5 bonds, which is how many electrons max? 10. So that's why phosphorus can hold more than 8. How many? 10 more. That's how it works. Now you want to try another example, I can show you all also. Okay, as you're copying, you can take a look at this other example as well. So the idea is that electrons don't like to be with each other. They want to have their own group. Okay, so you can look at 3s2 and 3p4 as well. Okay, 3s2 looks like this. 3p4 looks like this. Right? And then don't forget there are vacant 3d orbitals. That's why I say over here, right? Vacant 3d orbitals. Because they're not being utilized yet, but they're still there. Okay, because of what we have learned. Okay, now guys, how many electrons here are not happy with their current state of living? 2. Can they move out? 10. So over here, this guy move to one room. This guy will move to where? The same room? No, that's damn stupid, right? Okay, you want to move here. Okay, so that's the second room. Guys, how many unpaired electrons are there? 6 unpaired is how many? You can form a total of 6 bonds. So later when you want to try some examples, bear in mind, sulfur can expand the octet until you get hold 6 bonds, which is a total of 12 electrons max. Now there's a very easy way to do this. Okay, sulfur has 6 valence, then you just times 2. That's the maximum. For phosphorus at 5 valence, just times 2. Okay, you want to do chlorine also again. Chlorine got 7 valence, so what's the maximum? 14. Yeah, okay, these are the more common elements that we look at. Cancel over. Yeah, okay, so that's the reason how, that's basically how expression of octet works. Okay, they will not test you this, but it's very good to understand this. Okay. And with that said, hello, let's look at some dot and cross examples before we move on to what we need to go through today. Okay, so you can turn over to the, yes, that page. What page is that? Okay, 21, right? Okay, go to page. Oh, yeah, 21. Okay, go to page 21. Let's draw 4 examples. Okay, the rest you're going to try yourself. Okay, so I need you guys to try carbon monoxide, sulfate. What else? Okay, you're going to try these two first. Yeah, see which one you all can try also. Okay, not 21, 27. Yeah, again, 27. Those examples are on page 27. I bet. Okay, then you try XeF2, ClO3 minus. Okay, let's try these 4. Carbon monoxide is a little bit tricky, so if you can't do it, never mind, try the rest. Okay. Try these 4 examples. Once we get this out of the way, we can finally move to the whole idea of today. Okay. Looks correct, looks correct. Yeah. You don't spend too much time on the carbon monoxide because it's a bit wonky. Okay, the rest are more normal. And think of what a -2 charge says as well. Okay, I only tell you guys minus charge and plus charge, but I never include the number yet. You got -2, got -3, that kind. Think try it. Okay, don't forget the bracket and the 2 minus charge. Okay, perhaps I'll go over sulfate first. Okay, we kind of need to move past this A set, right? Okay, guys, we discussed the -2 charge. What does the -2 charge tell you? Any idea? Okay, you add an electron, right? Okay, but you add to who in this case? You add to oxygen, because oxygen is more electronegative. Okay, so let me give you guys the 2 options. Do you take 2 electrons and you give it to 1 oxygen? Or do you give 1 each to 2 oxygens? Okay, so the answer here is to make it fair. You have to make sure you split the 2 electrons across 2 oxygens. It has to be fair. So in this case, guys, you take a look at 2 oxygens that I'm going to add electrons to. How many electrons do they have now? How many valence? How many? Now it's 7 each, right? Okay, because you add 1 each. Okay, 7 electrons can form how many bonds? 1 bond. Okay, so immediately just draw a single bond for both of these guys. And then you can move on to the other 2 oxygens. How many valence do they have? 6. 6 can form how many bonds? 2 bonds. So with 2 bonds, just do immediately over here, fill out the rest. 2 bonds, fill out. So all okay. So we've settled everything on the sides. Now we come to the center. Anything else to add in the center? No, right? Because sulfur already has, you have already drawn 6 crosses. But with this many electrons, is it possible? Can sulfur hold this many electrons? Yes, right? Like what I've explained earlier, sulfur has the ability to expand its octet, okay, to 12 max electrons. Why? It has vacant 3D orbitals that are energetically accessible. Okay, I haven't really explained what energetically accessible is yet. All you need to know is that the 3s, 3p, and 3d subshell drive, okay, have very similar energy levels. Because their energy levels are so similar, electrons can just hop from the 3s to the 3p, 3p to the 3d, something like that. If the energy levels were very different, do you think the electrons can hop across? No. Okay, so because of the fact that it's energetically accessible, this can happen. So I forgot to talk about that just now. Like that. Okay, so you can take note of that. And then perhaps right, just go over carbon monoxide as well, since you guys have tried it also. Okay. Okay, carbon monoxide is a bit different because you don't have a central atom, right? Okay, if you have no central atom, you need to decide how many bonds you want to put in the middle. Carbon can form how many bonds? Carbon can form 4, right? Oxygen can form how many? 2. 4 bonds and 2 bonds, which one makes more sense to put in the middle of these two guys? It makes sense to put 2 bonds, right? Okay, 4 bonds is a bit too much, right? Okay, so for 2 bonds, let me just do a double bond each, and then I have lone pair here, carbon and another lone pair here. Okay, can? Now let's check. Oxygen has 8 valence. All agree? Carbon has how many valence? After bonding, it has a total of 6. Now, you see 2, 4, 6, right? Okay, is it possible to have less than 8 valence? Okay, like what I've mentioned, it is possible to have less than 8 valence, but there is actually a better way to do this question. Okay, what I'm trying to say is it's actually possible to make both of them fulfill octet. How? Any idea? Okay, so I want you to notice something. This guy has 6 electrons, this guy has 8 electrons. Okay, so we want to make both of them 8, 8. Now, do you notice something? Oxygen has 2 lone pairs. The lone pairs means what? It's not doing anything, right? Can we put him to good use? What can we do? What can we use this lone pair for? Okay, can you all see, right? We can actually now take this guy and put it up for sharing. So this is what kind of bond? Dative bond. Now you take a look, if you put it up onto the plate for sharing, right? Now, both of them have 8 valence. Just by doing this, carbon has 8, 1, 2, 3, 4, 5, 6, 7, 8. So now, right, you have to imagine the middle is up for sharing, so both of them will have that number. So both of them will have 6 from the middle and then 2 at the side. 6 from the middle, 2 at the side. So that's why carbon monoxide, right, actually looks like this. Double bond and dative bond. So it's a triple bond actually. So carbon monoxide is rather interesting, okay? In a couple of chapters when we start to learn this topic called enthalpy, right? Okay, you need to know that carbon monoxide is a triple bond. Okay, just know that as a fact. Okay, a lot of people think carbon monoxide was a double bond, me included last time. Okay, but no, it's triple. Okay, good. Okay, so with that said, okay, let's just very quickly go over the rest as well. Okay, give another like 2 more minutes, right? Okay, go and try whatever you can try first. Because I need to ASAP move over to the next concept. Right? Right for XEF2 on the ball. Fluorine can form one bond each. Okay, but xenon has how many lone pairs? Huh? Okay, you should have 3 lone pairs. Xenon has 8 valence, 2 of which used in bonding, so you left 6, right? 6 is 3 lone pairs. Can see that? Okay. So it looks a bit odd, but later when we talk about VSEPR, right? Okay, you'll see more of these shapes. Okay, but anyways, okay, last one is ClO3 minus. The principles are all the same, but we've done it a lot of times already. Minus means you add an electron to to the oxygen, sorry. Your oxygen has 7 valence, which forms a single bond. The other 2 oxygens have 6 valence. You still form 2 bonds. 2 bonds, 2 bonds. Anything else to fill in for the center? Okay, chlorine has 7 valence, now only drawn 5, right? So it has a lone pair. Okay so far? Yeah. Okay, so that's that. So whatever that we've done so far, right? Okay, is only 30% of the concept. Okay, this entire board over here is the summary of dot and cross. Everything you need to know. Okay, but it's only 30%. Okay, because we're going to use all that we've learned now, okay, to talk about this thing called VSEPR theory. One of the most important things in this chapter. Okay, so once you're done, right, okay, you can basically look at the following page. There's 2 questions there, okay, on that page, right, but that's not that important, okay, you can just answer yourself first. Okay, we just turn over to the next page. Okay. So go over the page 29. Now I'm going to be discussing this new idea. You can just read through it a little bit first. So VSEPR. Now you have to understand why we are studying this thing first. So currently, guys, we have drawn dot and cross diagrams, but we haven't accounted for one thing yet. We're only concerned with all the electrons and all that, right? Okay, but now we're going to look at this thing called VSEPR theory, which serves only one purpose. Okay, VSEPR theory aims to determine the shape and bond angle of a compound. Right now, we have only just drawn the shape. We have anyhow just placed the atoms like this. Okay, but now we need to account for shape and bond angle. The reason why this is difficult is because there are a lot of shapes and bond angles. You can already see a bit on the next page. Okay, but we start with the definition first. There are 2 definitions. I'm gonna write down the whole thing and then we break it apart. Okay. Electron pairs arrange themselves around a central atom, okay, as far apart as possible. Okay, as far apart as possible to minimize mutual repulsors. Okay, I don't think I need to explain the concept itself, okay, because it literally speaks for itself, right? Electrons never like to be close to each other because there's going to be a lot of repulsions. So they want to be as far apart as possible. Okay, so I want to break down a few things. What's electron pairs? Electron pairs is an umbrella term for both bond pairs and lone pairs. We're going to call that these 2 terms from now on. Guys, you all know what a bond pair is? Yes. Okay, bond pair is just a bond. What's a lone pair? Okay, so do know a bond pair is an electron involved in bonding. Lone pair is an electron not involved in bonding. You should know all that by drawing all this way. Okay? So they arrange themselves, next thing you highlight, around a central atom. Basically, when we determine shape and bond angle, right, you must only look at it from the central atom's perspective. All the side atoms don't have shape. Okay, as far apart as possible, yes. Okay. Why do you want to minimize repulsions, guys? Okay, sure, they want to minimize repulsions, but what benefit does that bring? So that the compound is more stable. Yes, exactly, guys. The whole idea of minimizing repulsions is to maximize stability. Okay, write it down as well. I think it's a very good idea. Okay, to help you really understand why we are doing all this in first. Okay, they want to stay as far apart as each other so that there is the highest stability. Okay, compounds always aim for the highest amount of stability. So that's what they will do. Right? So we show examples later. Okay, then the second thing is this one. Okay, the strength of the repulsions will differ. Okay, let's rank them. Okay, so if they ask you to state the definition, right? Okay, you need to state both definitions on that. Okay, don't just state one. Okay, lone pair, I'm gonna coin it as LP. Bond pair, I'm gonna coin it as BP. The strongest repulsions is between a lone pair and a lone pair, followed by lone pair and a bond pair. The weakest repulsions is between bond pairs. Okay, you can write this acronym as well. Okay, but now what I'm gonna explain is why. Okay, you don't really need to know why a lone pair repels more than a bond pair, but I think it's good to know instead of just accepting things, for how it is. Okay, so the main idea is that lone pairs, right, guys? Okay, I want you all to understand lone pairs are very close to the atom. Okay, they are closer to the central atom. But on the other hand, bond pairs are relatively further from the central atom. Why? Okay, so if you try to understand this, we have a covalent bond, right? Something like this guy. You have to understand that a covalent bond is like two people making a transaction. Okay, so this one, right, you're giving one. Okay, imagine this. Okay, they have one cookie each, then they share, right? That's a covalent bond. Alright, if you want to share your cookie with someone else, you have to like extend your hand and give him the cookie, right? So it's further from you, right? Okay, but then you look at fluorine. Fluorine has how many lone pairs? Fluorine got 3 lone pairs. This guy has 6 other cookies, but he hide it. He keep it from himself. Okay, so he put it in his pocket. So clearly it's much closer to him, right? Okay, so that's the idea. He only share 1. But then he actually has another 6 more that he don't want the hydrogen to see. Okay, so it's like lone pair, you're keeping your money to yourself. Okay, but then your bond pair is like you're going to share the money with someone else. So you're like, sticking your hand out so that it's a little bit further from you. Okay, that's the idea. Okay, and because you are closer, right, you're going to repel more. Okay, and if you are further, obviously you're going to repel less, right? Okay, so that's why bond pairs have the weakest repulsions, lone pairs have the strongest repulsions. Something like that. Okay, so as long as you get some sort of idea to accept this. Okay, but I don't need to know that. Oh, good. Can? Okay, we're gonna actually go into the shapes now. Okay, so I'll go over every single shape. Okay, as much as I don't want to, okay, as much as I hope that this is in a data booklet for you all to just copy and paste, this is not. Okay, so you need to remember all these shapes eventually. Okay, when I first did it last time, I was like, holy shit, this is impossible. Okay, but actually can. I'm gonna give you guys more information. So I need you all to basically dog here your 30 and 31. Page 30 and 31 is like you'll be referring to it a lot. Eventually, we're going to stop referring to it, of course. Okay, you don't have this in the exam. So, let me show you guys what is necessary for all this work. I'll start off with the easiest one first. Okay, you all see how the table is like, the number of bond pairs and the number of pairs. I'll start off with the easiest, 2 bond pairs. I don't care about lone pairs yet. Let's use an example in the notes. Okay, so Cl, BeCl. Guys, does it make sense? Okay. These 2 bond pairs, are they the furthest apart from each other? This is the furthest they can go, right? Okay, so imagine if this is one bond pair and this is another bond pair. Okay, do you think this is the furthest that they are apart? No, right? Okay, they can go further. And we know that the furthest, logically speaking, right, is a bond angle of, what's this? 180 degrees. Okay, so this is not very easy. Okay, it's just called linear. I'm sure you know what is called linear. Okay, it's straight line. And guys, I need you all to also include something else. This is a 2D shape. Okay, you will need to know which shapes are 2D and 3D. Okay, because it helps you with visualizing. This entire table, as long as you can visualize, right, then I'll just move on. Okay, later the visualizing will come. Okay, so let's expand on this. Instead of 2 bond pairs, we're gonna increase it to 3 bond pairs. Guys, 3 lines. 3 lines, right? 3 bond pairs. What's the furthest they can be from apart from each other? Okay, it's like take a circle, and then you have 2 bond pairs, right? It's like 1 line across. Okay, but then you now have 3 bond pairs. Can you see it's like splitting a circle into 3? Okay, when you split a circle into 3, this is the shape. Can someone tell me what's the bond angle? 120 degrees. Okay, as you can see, guys, all 3 bond angles are the same here. 120, 120, 120. Just like up here, the top is 180, bottom is 180 as well. Why is that possible? Why is the bond angle such a nice number? Because guys, I ask you all, there are no lone pairs here, correct? There are only bond pairs. Bond pairs, do they repel equally or differently? equally, right? Because they're all the same type. Lone pairs repel more. So now that we are going to introduce a lone pair, it's going to be a bit. Okay, so take a look out, guys. Okay, so this one, let me just introduce some other names as well. This guy is called trigonal planar. Trigonal, just remember because tri is three, right? Okay, I need to highlight the word planar. Planar is 2D. Okay, I want you to also annotate all the bond angles in the diagram because the notes, they never put it in the diagram, so you need to know where to put it. What does planar mean? Planar means lying on the same plane. So imagine this, imagine this flat piece of paper or this iPad here. If I were to take a 2D molecule like this guy and I slap it onto this paper, right, it will be completely flat also. It will not be like sticking out and shit, okay, no. So if I slap these two molecules down there, it will be flat as well. Okay, so that's what we call 2D. Make sense? And then I think this one should be fine, right? But now things are going to get a bit different. I'm going to introduce a lone pair. So instead of 2 bond pair, 3 and 0, I'm going to make it 2 and 1. Notice what I'm going to do here. I'm going to replace the top bond pair with a lone pair. Okay, so let's answer this question along the way. Guys, the bond angle, where is the bond angle? Okay, most of you guys will tell me here, right? Is this the bond angle? No. Okay, guys, I need you all to understand. Bond angle means the angle between bonds, not the angle between the lone pair. If not, they will call it a lone angle, which doesn't make any sense. Okay, guys, so take a look at this. From the past two examples, right? Here, here, and here, they are all 120 because they're all bond pair, right? But here, there's only between 2 bonds over here. So the bond angle must be measured here at 180. Our job is to answer this question. Why is it a bit different from 120? Any idea why? Okay. Any idea why over here the bond angle is not the same as above? By changing the bond pair to a lone pair, suddenly the bond angle becomes smaller. Hey guys, come back to this definition. We know that lone pairs repel more than bond pairs, right? So can I ask you, what's the repulsion type over here? Which one? This one is just bond pair repelling with bond pair, right? Okay, fair enough. But can you tell me what's the repulsion here? Here, the lone pair is repelling with the bond pair, right? Can I ask you which one is stronger? Lone pair, bond pair is stronger, right? So imagine this, okay? The top half, right, is repelling more, squeezing the bottom into a smaller bond angle. Does that make sense? As long as you can visualize, can already. Okay, same thing over here. Why is the top half and bottom half equal, flat? It's because they are both bond pairs. They repel equally. But do they repel equally with a lone pair in place? No. So if the top half repels more than the bottom half, can see, it will start to squeeze downwards. Okay, so that's how bond angles come about, because of different repulsions. Make sense? The name for this guy is as obvious you can get bend. Okay, and same thing, okay, we are still with the 2D shapes. Okay, so you put all these 3 molecules onto a flat piece of paper, nothing will be protruding out. Okay, so all these easy shapes. Okay, now let's move on to the more important ones. So far, so good? Okay, next. Okay, guys, I'm gonna increase the bond pair, lone pair to 4, 0. Now, don't look at the notes, come look at the board first. How will you put 4 bond pairs as far apart from each other as possible? What's the bond angle? 3 is 120. 4 is what? You think it's 90, right? Okay, so for a lot of the cases, we will think this is 90 degrees because clearly that looks like the furthest apart from each other, right? However, do not ever do this again. This is not the furthest they can go apart because it can go even further. Again, the definition says it's the furthest apart as possible, and it will look like this: 1, 2, 3, 4. Okay, let me just put the atoms there. Okay, some of you may be like, what the hell is this, right? Okay, so come. First of all, let me look at the bond angle. It's 109 degrees. Can you all see? 109 is larger than 90. So it's actually further apart, which will mean the repulsions are even less, which is a good thing. Can you see that? I need you all to imagine, I need you all to treat electrons as an intelligent species. They know how to be as far apart from each other as possible because they really don't want any repulsions. So you must trust them, they know what they're doing. Why are they so far apart from each other? Some of you may be looking at this and just go, hey, isn't this an acute angle? How is this possibly 109? Because let's introduce the idea here. This is a tetrahedral shape. And the tetrahedral shape is known as a non-planar shape. Let me write this down. Guys, non-planar means what? Planar means 2D. Non-planar means 3D. Guys, this is where the visualization will take place. You need to understand whatever that you're looking at looks like it's 2D, right? But it's not. So how does this shape actually look like? Okay, I want you to imagine these 3 legs at the bottom, right? Have you seen a tripod before? You know, a camera. A tripod looks like this, right? You look at your fingers. Okay, do you think this is flat, this 2D? No, okay, it takes up all 3 dimensions, right? Okay, and because of that, you have to imagine the 3 legs are pointing like that, and then the bond at the top is just upwards like this. So that's why it's a 3D shape. Okay, the electrons are intelligent enough to arrange themselves in this manner because this is actually further than 90 degrees, as you can clearly see here. So what we're going to do first, guys, okay, your notes in school might have this notation. I want you to draw this notation out. Okay, this shape can possibly look like this. I'm going to teach you another way, right, of drawing 3D dot and cross structures. Not dot and cross, but 3D structures in general. And I want you all to write the legend for what this represents. This right here is a bond that is pointing outwards. The dash one, right, is a bond that is pointing inwards. I'll visualize with you guys again, don't worry. Okay, but draw this out first. Because later I will let you all play around with this kind of drawing. So as you're copying, I'll just listen about, okay, this is a 3D notation. They had to come up with a notation, right, so that we can read 3D structures on a 2D piece of paper. Okay, you will see this in your RI notes, definitely. Okay, RI definitely have. Okay, so it's good to know this now. Okay, all good. Come on, let's visualize together. I want you all to pay attention to the 3 legs, the tripod legs at the bottom. Don't care about the top yet. Can? Okay, look at my fingers. Again, the tripod looks like this, right? Can you all see my middle finger is along the whiteboard, so it's a normal board. But my thumb is this guy. Can you all see he's pointing outwards towards you? So that's why pointing outwards. Finally, look at my index finger. Can you all see it's pointing inwards into the whiteboard? It's not along the whiteboard. Okay, maybe the angle will be different. Okay, but it's pointing inwards, right? That's why it is this board. You see that? So you must treat it as if it's a tripod stand with a stick on top. Yeah, again, that is tetrahedral. Okay, and I need you all to understand. You look at your finger like that again. I know here it looks like an acute angle, right? But because this is pointing outwards, the angle is actually 109. Don't worry, all the angles here are the same. This is 109. This is 109. This is 109. This is 109. Everything here is 109. Okay, because of the protruding outwards, that's why it's not an acute angle. It just looks like it. So you must get across that 2D barrier you have in your head. Can first? Okay, very quickly, let me just finish up the other 2 shapes first. Okay, let me answer some questions. All okay? Okay, instead of 4, 0, I'm going to change it to 3, 1, and I'm just going to change the top to a lone pair. So all I'm doing over here, right, is this. And again, guys, can I trouble you guys to draw the 3D notation? Can you all see here the tripod legs are still there? Okay, so go ahead and draw this. This is still pointing out. This is still pointing in. Can you see that? This shape is called trigonal pyramidal. Why trigonal? Tri. Because there's 3 bond pairs. Can you all see? Does this look like a pyramid to you guys? Kind of, right? I don't know. Okay, it kind of looks like a pyramid, right? Okay, so just I don't know, convince yourself there's a pyramid because you have no choice anyway. Okay, so you convince yourself there's a pyramid, you look like a pyramid, then you remember better. Okay? Anyways, guys, the bond angle here is 107 degrees. Okay, is this the bond angle, by the way? Here? No, bond and lone pair, where got such thing? Okay, it should be between 2 bonds. Can we just very quickly explain why is the bond angle smaller? Can you tell me why? What's the type of repulsion here? Go and annotate. I need to see your thing completely messy. Okay, so what do we have here? The top. This is bond pair repelling with a bond pair. Over here, what do we have? Bond pair repelling with a lone pair. Again, which one is stronger? The one at the bottom, right? So can you see if the repulsive forces on top are stronger, right, it will squeeze the bond angle smaller. You can see that? Yeah, as long as you can see, can already. Because your explanation is literally just tell me it's stronger. Okay? Squeeze the bottom. Can? Can, is this planar or non-planar? It is literally the same tripod as the tetrahedral, right? So go and write this down. It's a non-planar shape. Some they will test in non-planar 3D. All good. Finally, let's move down to 2, 2. 2 is actually your water molecule. And guys, have you seen this shape? What's this shape called? It is the same as just now. It's actually your band shape. And it's band 2D or 3D. Okay, band is actually a 2D shape, just like what I've explained earlier on just now. Guys, can you all predict the bond angle here? Okay, smaller or bigger compared to what we saw just now? Here is bond pair, bond pair. Here's bond pair with lone pair. Here's what? What's the repulsion type in this case? Can you all see the top half? This is lone pair repelling with lone pair. And this is the strongest repulsion. Because the repulsion is the strongest, the bond angle is the largest or smallest? Smallest. The repulsion on top is very strong and they squeeze the bottom until very small. Okay, so here, bond angle is only 105 degrees. Okay? Now guys, what's a very good way to memorize this? 109, 107, 105. What's the pattern over here? The pattern is just -2, -2. That's it. Okay, so minus the values, then you can. That's the easiest way to remember. All good so far? Can, so far, any questions? All good. Can? Okay, come. Let's turn over to the next page. Okay, bear with me. I really need to go over every single shape. This is where the shapes get a bit more interesting also. Okay, you can also see page 31, page 32. Page 32, the questions I already go through with you guys over here. We don't have time to go and separately do it. You want to transfer, you transfer it over yourself. Okay, look at page 31. Okay, this is where shape gets kind of real. Okay, so not to say that's not as important. Unfortunately, all these shapes are important. Okay, so start with 50. Guys, 50, what I want you all to do, okay? Can you go color code the structure also? Okay, so use highlighter or whatever. Okay, what I'm going to do is this. I'm going to put these 3 bonds in red. And I'm going to put these 2 bonds in black. There's a reason why we're doing this. It really helps. Okay, so do all this one. Okay, let's get the basics out of the way first. This guy is called trigonal bipyramidal. Just need to memorize. Shape, okay, sure. But look at the bond angle on the notes. You will see 2 words, axial and equatorial, right? Guys, let's look at the word equatorial first. Where does the word equatorial come from? Comes from the word equator, right? Guys, you all know what the equator is on the planet? Okay, we're going to use that as an example. Okay, I'm going to draw Earth. The equator is obviously here. It's flat, right? The flat part of Earth, right? Okay, so guys, I want you to understand the equatorial part is basically the red color bonds. The red color bonds. So if I put it on Earth, it looks like that. Flat. Can you visualize? Okay. Can I ask you, between the red color bonds, what's the bond angle? You see the Earth, you take the circle, you divide into 3. So it's what? 120 degrees. Understand this first, right? Guys, that was axial. Axial is basically the North Pole and the South Pole. Can you see that? Okay, and we don't care about bond angle yet, wait. Guys, I ask you, is this shape 2D or 3D? The whole thing. Okay, Earth is not flat. Okay, Earth is a sphere, right? Unless you're a flat Earth believer. Okay, so anyways, yeah, so this whole thing, where right now, it's non-planar, obviously. It is 3D. Right, cancel that. Right, okay, so you take a look at this. Can I ask you, don't need to look at the notes here. The axial place, the North Pole, South Pole, what's the bond angle? Wait, what's the bond angle between the North Pole and the South Pole? You will tell me is 180, right? Okay, but look at the notes, what they say. 90. Why is it 90? Because I need you all to be very clear with this. Bond angle is the angle between the closest two bonds. Guys, I ask you, the North Pole, the next closest bond, is it the South Pole? No, that is what? One of the equatorial bonds. You can see that? So I ask you, North Pole with the equator, what's the bond angle? Can you all see that the equator and the North Pole is perpendicular one? Okay, so over here, it's actually 90 degrees with respect to all three equatorial bonds. That's why here, right, axial is actually 90 degrees. You can see that? Don't tell me 180, okay, no, it's the next closest. So far, so good. This shape, they will test. Very important. If you can't visualize, if you think it's a 2D shape, I'm sorry, the whole question wrong. Okay, now guys, can I trouble you all, right, to redraw this compound, but including this. Right. You might want to use the Earth as a reference. Change that. Okay, I tell you all, you only need to change two bonds into this and this. Go and try. Only two. Okay, so redraw it. Yeah, I can tell you your school won't go through in detail. This in detail for all these shapes. They will just tell you it's like that, then just accept it, then just memorize. Okay, ask yourself which bond is pointing towards you and which bond is pointing away from you. Okay, good. Okay, only need to change two bonds. Okay. Okay, all good. You need to go through. Okay, that one is okay, but there's a better way of doing it. Okay, come, let's take a look. Okay, you want to look at this. Can you tell me which bond is pointing outwards towards you? Can see is this one. This point is pointing towards you, right? So the one that's closer to you, towards you, draw this version instead. Then which one is pointing away from you? Okay, so I hope you realize the one pointing here is actually along the board. Okay, this one's actually pointing inwards. So it's this one, they should point inwards. So they should usually be together, one pointing out, one pointing in. So it's quite obvious. Okay, and then we practice a bit more of this later. Right? The rest of these shapes, right? Okay, it's kind of built off this, so I'll go over it very quickly. Okay, so the next one after 5-0 is 4-1. Then for 4-1, right, they actually changed the bond pair into a lone pair. So I hope you notice I'm going to use the same color coding and draw this. So I hope you realize, right, it's just one less thing over here, then just replace it with a lone pair. Okay, so this is the lone pair, and then North Pole, South Pole. Guys, 2D or 3D? Still 3D, right? It's not flat. Okay, so this is called seesaw. They ran out of names. Yeah, they gave up, right? So they call it seesaw. Okay, so anyways, you can call this non-planar and 3D. Okay? As for the bond angles, you notice is the same as whatever we saw just now. Because the equatorial is still 120. Now, I know some of you may be asking, how come these two will not become 180? Okay, but take note, okay, in this case, because of the fact that there's a lone pair, right? Okay, somehow they observe, right, the bond angle still maintain 120 degrees. Okay, these are not really the key point. Okay, as long as you all can understand the first shape, right, the rest will follow the first shape. Okay, that? Yeah. Right, so it's not much, okay, just give me more of the bond angles. Okay, the next one is important. Okay, next one is important. Okay, it's 3-2. 3-2, right, is, again, they ran out of names, they legit just gave up over here. They call it shape. Okay, doesn't take a genius to figure out why it's called shape. Okay, but yeah, 3 bond pairs, 2 lone pairs. Now just take note, a T shape is actually planar. It's actually 2D. Okay, that's why I have to draw all the solid and the dash bonds. Okay. And doesn't take a genius to also figure out that the angle is 90 degrees of freaking T shape. Okay, so next time you see T shape, please don't get it wrong. Okay, it's very obvious. Okay, can. Okay, the last one is very simple also. It's 2, 3 lah. You will notice you just decrease the number, then you increase the number. So 2, 3, right, is actually what we saw just now. 2 bond pairs, 3 lone pairs. Okay, just now you all draw XEF2, right? Then you all saw that were 3 lone pairs. This one, right, again, they just observe that the shape is linear, it's 180 degrees, and we know linear has to be a 2D shape. And yeah. Yeah, okay, some of these shapes, I think this one not that much. Only the first one and the third one is a bit more important. The second and the fourth one, yeah, just a bit not much for me to discuss. Okay, but when we move on to 6, right, that one actually more for me to talk about. Okay, so almost there already, I'll just bear me. I know there's a lot of shapes. So far, any questions? Okay, one last thing to go. Okay, one last stretch. Okay, I will now increase it to 6. And 6, surprisingly, there's actually less to start. You don't know why, you just accept it. Okay, for 6, right, we're gonna start off with 6-0, obviously. And for 6-0, I only want to color code your structure again. Okay, because it's not it doesn't look like what it looks like. Okay, so here, these are in red. Okay, these are in red. And then these are in black. I'm going to use the same planet analogy again. So the planet looks like this, right? Okay, we have the equator that is in red, and then the North Pole and South Pole in black. Okay? Okay, if there's an equator and an axial plane, right, then why do they only have one bond angle there? Okay, let's figure this out together. Okay, first of all, the equator, right, is just 4 bonds on the equator. And then there's North Pole and South Pole. Can I just trouble you guys, right, to go and redraw this compound using these arrows? Okay, draw the same thing but with the 3D notation. Okay, can you all see these two at the front are pointing outwards towards you? Okay, so these two, right, should have the solid bonds. Okay, and then the other two are pointing to back, right? So that's why you change these two to this. Can I know it is something new, you all need to get used to this notation. Okay, can I ask you all, right? We look at it one by one. There's still an equatorial and an axial. Okay, what's the bond angle in the equatorial plane? Okay, what's the bond angle? Hey, wait, I thought if you have 4 bonds, the furthest you can go is actually 109. Remember this shape? Why here is it only 90 degrees? Think, I thought 4 bonds can go up to 109. How come here only 90? Am I contradicting myself? Okay, no, actually, what's the reason? Guys, You'll notice just now under tetrahedral, right? I had the freedom of using all three dimensions. But then here, equator is how many dimensions? Equator is flat, right? So because equator is only two, I'm only restricted within two dimensions. That's why I can only, the furthest I can go, right, is 90. But earlier on, right, there was no restriction. So here, if you can utilize the third dimension, right, you can actually go further apart into 109. This is the configuration. Does that make sense? Here we have no choice lah. Okay, so 90 is the only way because we only have two dimensions. Make sense? Okay, so guys, axial plane there, what's the hypotenuse angle? It's still perpendicular to the equator, right? The next closest one, right? So it's also 90 degrees. That's why over here they just lump it together as 90 degrees, even though you can actually split it into two. So understand, okay, this is the most important part. Okay, having different number of dimensions will allow you to have different arrangements of the electrons. So don't get it confused. Don't just think, oh, four bonds must be 109 degrees. No. Okay, it's all about whether it's planar or non-planar. So overall, guys, this shape is called octahedral. Is it planar or non-planar? You can clearly see it's Earth, right? Earth is non-planar, right? It's 3D. Can? Then let's move on to 5-1 very quickly. 5-1, all you need to do here is to get rid of the south pole. Okay, so remove the south pole and you only have the north pole. Okay, then there's a lone pair over here. So there's nothing much here, guys. Without the south pole, right, it's still 90 degrees. This guy is called square pyramidal. Honestly, when you see the word square, just do me a favor, guys. You see the word square, just put 90 degrees. Don't you think so much? Okay, I mean, you should know why I've already drawn the Earth diagram for you guys. But square, just put 90. Don't think so much. Okay, then finally, okay, it's still a non-planar shape, obviously. Because you have a freaking equator plus a north pole, right? But the last shape is actually rather common as well. The last shape is 4-2. Okay, and for 4-2, I removed the north pole. So I hope you all can see what is shape here like. Two lone pairs. Guys, can I ask you all, is this planar or non-planar now? I only have the equator, right? I have no more north pole, I have no more south pole. And the equator is flat. So guys, that's why this guy here is called square planar. The word planar already implies it is 2D, and the word square implies it's 90 degrees. Very common shape, by the way. 6-0 and 4-2, very common shapes. 5-1, I don't really see all that. Okay. This one have north pole, south pole. This one have north pole. This one have no poles. No poles meaning only the flat equator. Make sense? Okay. Yeah, so those are all the shapes. We're gonna apply these shapes in questions also. Okay, for like the first like 1 or 2 months, you need to refer lah, definitely. Okay, but you must slowly start to refer less and less. So guys, let's turn over. Okay, we take a break soon. Okay, turn over to page 33. I'll show you guys how to derive all the shapes. What are the required steps? We look at part 1 first. Okay, SO3. Now the very first step is to draw dot and cross. Because you guys just started, okay, eventually you can skip this step, but now draw dot and cross first. Okay, you see, if you don't know how to draw dot and cross, I'm sorry, the VSEPR, there's no chance. So number 1, guys, for SO3, go ahead and draw the dot and cross diagram first. Okay, then I'll tell you what are the other steps in a bit. Okay, so dot and cross diagram should look like this. Okay, you don't have to care about the shape yet, because you don't know. Right, okay, so oxygen is double bond, oxygen is double bond. Just double bond for everything first. Okay, that's what you can be doing for now. Okay, fill out the rest of oxygen. Is there anything else you need to fill in on this sulfur? No, right? Because sulfur has 6 valence, I've drawn all 6 already. Make sense? Then what next? Okay, so once you have finished the dot and cross diagram, okay, the sulfur can hold 12, okay, that's possible. So you leave your answer. You shouldn't have any native bonds. The second thing is to count the number of bond pairs and lone pairs. Because clearly, guys, you saw so many configurations. The number of bond pairs and lone pairs give rise to different shapes. So can someone tell me how many bond pairs and lone pairs there are here? Okay, how many bond pairs and lone pairs? Okay, obviously 0 lone pairs, right, on sulfur. Guys, remember, the definition says central atom, so it's always in the center. Don't care about oxygens on the side already. How many lone pairs? 0. How many bond pairs? Now you guys tell me 6, but that is wrong. Okay, so I need you to think of this. Double and triple bonds are considered as one bond pair. Very important. Why? Because guys, if you count it as 2 separate bond pairs, you're implying that they will repel away from each other. Do you think the bond pair is gonna? Do you think the double bond is gonna like repel from each other, split into 2 single bonds? No, doesn't make sense. So that's why you count it alone. The double bond will be together, so it's one group. Okay, very careful. I'll be very careful with this. So guys, how many bond pairs? How many lone pairs? Could be 3 bond pairs and 0 lone pairs, right? And with that, that gives rise to what shape? Okay, so for now, just refer to it. I'm sure you all know how to take 3 bonds and split them apart equally from each other, right? Because there's no lone pairs here. So we can split them apart into a 120-degree bond angle. So you just mentioned this is trigonal planar. Now let me show you guys the mark allocation for this one question. Okay, so trigonal planar, draw something like that. That is the full structure with the shape included. Now let me tell you something. Okay, when you draw this full structure, right, the side atoms don't need to draw lone pair. I say first, that's why it's very clean. The whole purpose is clean, right? Okay, you only need to draw the lone pair in the center. Okay, but now don't have now, so don't need to draw anything. I'll show you the marks. Shape, 1 mark. Bond angle, 1 mark. Final structure with the shape included, 1 mark. 3 marks. Just for 1 part. Okay, I'm gonna let you guys try some more examples as well. Okay. So go and try it. Part 5 and part 6, ICl3 and SO2. Go and try. Okay, in the end must fulfill everything. Shape and bond angle and the structure must be drawn. Yeah, just send some. Okay, I know some of you guys are asking for the redox tutorial from your school, like some of the hard questions, the answer, right? Okay, so I'll just send you guys the answer there. I worked out the answer already, then you'll just get it with explanation and all that. So I think I send most. Yeah, okay, send everyone already. Who haven't just sent? Yeah, lah. So in case you need it, just follow. All right. Okay, so let me just draw some of the answers. Okay, so for ICL3, you should have a P shape, 90 degrees. Okay, that's how it looks like. SO2 to look like this. No daily bonds are, by the way. Okay, this is a bend shape at 118 degrees. Okay, this is the bend shape got two types, so just be very careful with the bond angle. Okay, if you have two lone pairs, then it's way smaller. This one lone pair is bigger. Okay, and you can make a comparison as well. Okay, like if you look at the two bond pairs, like water, why does water have a way smaller bond angle of 105? They can ask questions like that, and all you need to do is just to tell me what kind of repulsion it is. This is a lone pair bond pair repulsion, but this is a lone pair repulsion. I'm sure you all can see if the repulsions here are way stronger, it will squeeze the bottom to a smaller bond angle. That's why it's 105 compared to 180. That's just another way you can compare band shapes, which is one of the questions that it was in the notes just now, but you all can just write anywhere you need. Okay, anyone have any issues with this? Okay, so when we do the tutorial in the next lesson, like 2 lessons later, okay, there will be some questions where you need to work out 4 different options because MCQ or 4 options, and then you need to do all this 4 times within the span of that one MCQ question. We'll get there, we'll get there, okay, no worries. Okay, any issues? No? Right, okay, I'll go over one more small little segment here, is electronegativity. Why I say it's a small segment is because we did technically go through a bit of it already. Afterwards, okay, before the final segment, we'll take a short break. Okay, so for now, let me just cover a bit more. Okay, any last questions for VSEPR? Okay, do I have? Can, right, okay, nice. So the next thing on the agenda is electronegativity, which I don't really have to go in depth because you guys already know that covalent bonds if you have different atoms, they are playing a game of tug of war. They are always actively trying to attract electrons to themselves. You can even see that in the definitions. The main keyword is the word attract. Attract a shared pair of electrons towards itself. It's a game of tug of war. Okay, but that will be all learned already. And the next thing is, you all see, they ask you to explain why electronegativity increases across a period. Now, this is an atomic structure concept because we learn physical trends in atomic structure. So I'm not going to go through that now. I don't think I have the time to go through this. Okay, so it's just your effective nuclear charge and all that stuff. Okay, so if you did watch the second atomic structure lesson, you should be able to answer this. It's physical trends, periodic table trends. Okay, so none of my concern here, this one's not important for today. Okay, but then the next page also says that down the group, right? Now, you guys need to know the trends, that's for sure. But you don't need to remember the explanation. Because imagine you in exam, right? Then you like recite the explanation in your head. The shit is not efficient, right? Okay, so how do we do this? Guys, what I want you to do is to draw a periodic table. Not the entire thing, no, as in you have to look at the periodic table like this. Guys, can I ask you where is the top 3 most electronegative elements? FON is at the top right, right? Okay, since you know FON is the most electronegative, I ask your inference skills. When you go across a period, electronegativity must increase or decrease? Increase all because you're going towards the highest range already. Then I ask you, down the group left, electronegativity must decrease all because you're going away from FON. And guys, I did tell you before, okay, maybe if you ever watched the lecture yet, never mind. But electronegativity, any periodic trends across a period and down the group are always same or opposite? Opposite. Okay, take note. You ever watch it? Never mind. Okay, you go across the period and down the group is always opposite. Not just electronegativity, but in atomic structure, you learn atomic radius, you learn ionization energy. Okay, so yeah, this is the way you can like compare all the different electronegativities and stuff. Okay, then we just quickly move on. Okay, go to page 35 at the bottom. That is what I want to discuss. Okay. Guys, we're going to talk about this thing called polar and non-polar bonds. Okay, new terms. Okay, so let's take a look at a bond that looks like this first. Cn. Can I ask you who's more electronegative? F. So F will basically steal quite a lot of the electrons to itself, right? The last time, okay, let me show you guys, you put it like that. But this is ugly. Okay, we don't want to do this. It's too ugly already. Okay, so what we want to do, just draw in the middle also. Okay, so it's nice. Okay, but there's another notation, guys. If fluorine is taking more electrons, right? Overall, does it have a positive or negative charge? Negative, right? Then carbon is losing electrons, so overall positive charge. But can we put an actual plus and a minus charge? Because is this an ionic compound? No. Fundamentally, guys, this is still covalent, right? So I need you to put this, okay? You cannot put actual charges. Okay, you cannot put the actual plus or minus charges. Okay, as electrons are still being shared. It's still a covalent bond. Fundamentally, it's about sharing of electrons. So we will use another type of charge called a partial charge, which looks like this. Looks like a musical note, like the quaver if you take music before. Yeah, okay, so it looks like this. Okay, I don't know how you draw it. If you don't know how to draw, then you just draw S. If you draw S, also can. Doesn't matter. Okay, S plus or S minus, or delta plus and delta minus. I call it partial plus and partial minus. Okay, there's many names about it. Okay, this is not an ionic compound. Electrons are still being shared. Okay, can? Okay, the another thing we're going to do is this arrow. We're going to draw an arrow that shows where the electrons are gravitated towards. Okay, since it's gravitating towards F, right? Okay, we're going to draw this arrow here. Guys, don't just draw an arrow because you might be mistaking it for a dative bond. So you need to draw this one line over here to distinguish it from a dative bond. Okay, this is what we call a dipole moment. It's a fancy name, guys. Okay, but that's all it is. It's just fancy. Okay, it just shows you where the electrons are moving towards. That's it. There's really nothing here. Okay, can guys, this is what we call a polar bond. So I ask you, a polar bond is a bond that has electronegativity difference. So can I ask you, what's a non-polar bond? A non-polar bond is a bond that has no electronegativity difference. Guys, what scenario would there be, right, where there is no difference in electronegativity? What scenario? If both atoms are the same, right? If they're the same atoms, they're not gonna take electrons for themselves. It's quite fair. So for example, we have Cl and HH. Quite clearly, the electrons are going to be right smack in the middle, right? But there's one exception. I need you to take note of this exception. CH is a non-polar bond. Okay, but why? I thought they have different atoms. Okay, the reason is very simple. Okay, it's because the electronegativity difference is so insignificant to the point where it doesn't matter. It's considered non-polar. Yeah, that's the only exception you need to draw. And because it's non-polar, you don't need to draw all this shit. Okay, what partial plus, partial minus, no need. Finish. Okay, not difficult, right? This part. Okay, it's just electronegativity. So what we're gonna do next, okay, I don't really care about bonds, right? Bonds are just a small part. What we really care about is the molecule. So we're gonna understand what makes a molecule polar or non-polar. Now we need to fulfill two things. Number one, no shit, you need a polar bond, right? If you don't have polar bonds, how do you expect it to be overall polar? Okay, that's not my point. My point is here. There must be an overall dipole moment. What does this mean? There must be an overall line. Okay, so take note, cannot cancel out. Later we use examples to explain. Okay. So you see, everything here is linked one because you look at the next page, right? We're just going to use examples to talk about this. Okay, so once you're done, turn over to page 37. Yeah, this segment legit very easy. Let's just get it over and done with. All right. Good, right? Okay, so take a look. We have, okay, we start with water first. I do water with you guys, and then the rest you do yourself. Okay, so number one, how to draw the structure of water? Go and try. When I say structure, right, I don't mean dot and cross. I mean the whole thing with the shape, you got the bond angle and everything. Okay, just shape. No need to draw bond angle, they never ask here. So you see, we learned VSEPR theory, right? Because it's linked to this concept. It all flows on, right? Okay, good. Nice, nice. Okay, good. All right, let me just tell you guys first. To save time in exam, right? There are a few compounds that you need to know their shape. You must know their shape. Like you shouldn't be working it out. You should just instantly, you should know it. Number one, CH4. Did they ask you to draw here? Okay, they didn't. Okay, but CH4, can you tell me what's the shape of CH4? Okay, 4 bonds, just 4 bonds. It's a very special tetrahedral shape, right? So I must know. It's like standard. Yeah, okay. Next, carbon dioxide. You know how carbon dioxide looks like? You know what the shape is? Okay, so this one, just gonna figure out yourself. It's not very easy to figure out. Okay, but I'll tell you all now first because these are shapes you just need to know by heart. Okay, you have no time to work it out in the exam. Okay, number 3, NH3. NH3, can someone tell me what this shape is? Remember? Okay, now probably can't remember. It's trigonal pyramidal because it kind of looks like a pyramid. That's the one that I've discussed earlier. Okay, last but not least, we have water. Water is over here. So yeah, water is your bend shape. So the reason why these are some of the most basic structures you need to like so-called know, right? It's because they are the most common shapes. Tetrahedral, linear, trigonal pyramidal, and bend. There's one more that is trigonal planar, but it's not here. Okay, so doesn't really matter. Okay, so for water, we have this bend shape. Okay, if you don't draw the low pair here, I don't. Okay, just draw that. Okay, so draw the low pair. Okay, now guys, who is more electronegative? O or H? Yeah, I'll drop here. Yes, okay, correct. Is to determine who is more, or whether the overall molecule is polar, right? So O must have a partial minus. H has a partial plus. Do the same thing for the other side, partial plus. Okay? All good? Okay, then where's the electrons going towards? In the bond. Electrons are gravitating towards who? Oxygen, right? Again, nice. Okay, so you move towards oxygen, put a line at the start. Okay, put a line at the start. Yeah, this is how you work it out. Guys, can you tell me, is there an overall dipole moment? Are these arrows eventually pointing towards something? Are the arrows cancelling each other out? No, right? Okay, so can see why. Okay, you all have you learned vectors before in secondary school? Okay, you all know vectors, right? You must you want to resolve vectors, you must put tail to head, right? Okay, so you put tail to head like this, and then you shift this tail to head looks like this. So overall, it is pointing upwards, can see that. So if it's overall pointing in a certain direction, doesn't matter what direction, right? If this has an overall dipole, it is polar. So water is a polar molecule. We need to know this well, right, for the next lesson. Okay, next lesson you must determine what is polar molecule, what's a non-polar molecule. Because we're going to expand into intermolecular forces. Yeah, okay. So y'all go and try the rest. Okay, this exercise y'all must try as well. Okay, so I'm not going to rush through this. Okay, this I'm going to try. but all the states must be accounted for. Okay, I'll just draw CH3F. So it looks like this. It doesn't matter where you put the F, honestly. Okay, you still end up with the same answer. Okay, I put F on top. You notice that that is the only polar bond, CF. Right? So the electrons are going towards the top. So guys, is that an overall dipole moment? Yes. Okay, so this is a polar bond. Okay. Okay, for carbon dioxide, I've already drawn the structure for you guys earlier. Okay. Oxygen is more electronegative than carbon, right? And then you notice that just going like this, right? Is there an overall dipole moment? No. In this case, because it's a linear shape, right, it cancels each other out. So this is non-polar. So carbon dioxide is a case of having polar bonds, but no overall dipole. So overall, it's still non-polar. Okay, the last one, go and put a star next to it. I'm going to try that also. CCl4 is very important. Okay, come, let's go over CCl4. Right, so CCl4 looks like this, tetrahedral shape. Right? Okay, so we know Cl is more electronegative than C. Okay, so split all your partial charges, and carbon is partial positive. Point in all the directions here. So guys, is there an overall dipole in this case? Is there an overall dipole moment, or are they cancelling each other out? Okay, so I hope you all realize okay, CCl4 is a special case because a lot of you guys will think that There are 3 arrows pointing down and 1 arrow pointing up. So overall it's pointing down, right? Okay, no. I mentioned that this is a 3D structure. Okay, 3D structure, right? These arrows are all pointing each other out. It's all pointing in all directions. So you cancel out in all directions. Make sense? All 4 directions, you will just cancel each other out. So tetrahedral shape is one of the reasons why. Let's explain for this question. What do you need to include in the inputs? First, you must tell me that CCl4 has a tetrahedral shape. Like that's the first keyword. The shape is what leads to this. Okay? It has a tetrahedral shape. Then you can tell me that the dipole moments of CCl cancel each other out in all directions. So it's a very common non-polar molecule of CCl4. You see that very commonly. They cancel each other out in all directions. And that's why there's no overall dipole. So it's just a non-polar molecule. Can you see this? Okay. Some keywords here, huh? This tetrahedral is the most important one, all directions. Any issues here? Okay, Right, we'll take a short break first. Okay, maybe 5 minutes. Okay, then afterwards, I'll go over one last concept. That one doesn't take that much time. Okay, so we're pretty much almost done for the period. Okay, can? Yeah, sure. Go to the toilet, whatever, no break time. Yeah. Let's talk about our final concept for today. It's only like 2 pages and then we are done. Okay, but this one is a rather interesting concept because we know that there's ionic bonds and there's covalent bonds, right? Okay, but to preface this first, guys, okay, it's not always black and white. In real life, it's not that simple. It's always a mix. Okay, so let's cover some ideas first. Ionic bonding is all about the transfer of electrons, right? Okay, whereas guys, covalent bonding is about what? Sharing. Now, can you all see they are polar opposites of each other? Okay, 2 completely different ideas. So you would think it's opposite ends of a spectrum, right? Okay, but as I mentioned, in real life, it's usually a mixture of 2 things. Okay, both ionic and covalent, in fact. So we have this thing called intermediate bonds, where it's a mixture of both transferring and sharing of electrons. So there are a few scenarios that showcases this. Okay, and perhaps an analogy of looking at this is as such. Hey guys, you all can think of transfer of electrons, right? You have a cation and you have an anion. Whereas sharing of electrons, as we talked about last lesson, is about the orbital overlaps. Make sense? Now let's come up with an analogy here. Okay, so you can think of it as this way. Okay, ionic compound is like a friendship between a guy and a girl, right? Okay, you can think of it as platonic friendship, right? They have nothing to do with each other. All they are just the opposite gender. That's it, right? Okay, but then the opposite of that, right, is when they are in a relationship, right, a couple. Okay, so platonic friendship versus a couple is opposite things. Couples, they like to share things, right? Okay, whatever is yours is mine, whatever is mine is yours, you know all that nonsense, right? Yeah. Okay, so it's all of that. Okay, but guys, is it that black and white in real life? Do you think this is very easy? Okay, love is complex, right? Okay, so guys, in real life, okay, we usually have this middle ground. I'm not sure whether you all see this term before. Situationships. Okay, so that's mostly the molecular world as well. What situationships? Okay, you like this guy, the guy probably like you don't know that, you don't know that, and everyone also, no one actually declare whether you all like each other or not. Okay, you're just in that middle zone. Okay, and that's exactly what intermediate bonds are about. So guys, let's present the first scenario. There are ionic bonds, but they are not completely ionic because they have a bit of covalent properties, or what we call covalent character. So how does this work? Now guys, they started off as ionic bonds, right? So they started off as platonic friends. But usually, you all know what happens, right? Okay, would they ever really be platonic? Really or not? Don't know, right? Okay, so eventually they start developing feelings for each other. You can look at this scenario here. Now imagine the plus charge is very high. Imagine the guy is very cute. Okay, if the guy is very attractive, right? Okay, the chances of you flirting with the guy is much higher, right? Okay, the chances of you developing feelings for this guy is much higher. So imagine that the girl is the anion. You can imagine this as no longer a perfect circle. You can see, right, that it's kind of attracted by the very, very high charge cation. Okay, so I say this again. The cation is very attractive. The guy is then cute, right? So because of that, there's a high chance the girl will start flirting with the guy. So she will get kind of attracted towards this guy as well. So in other words, whatever that I just shaded over here, this is electron sharing. As you can see, electron sharing is when they intersect with each other, right? It's kind of like this person over here. They kind of try to flirt with this guy. Alright? So to really get the idea across, okay, what's happening to this? What's this circle over here? This circle is what we call an electron cloud. The electron cloud is just a region around an anion where you can find the electrons. That's it. It's just a region of electrons. Okay, does that make sense? Okay, and because this guy is super attractive, plus attract minus, right? Electrons minus, right? Okay, so you will just pull the electron cloud towards itself. Does that make sense? So it's no longer a perfect circle when they have nothing to do with each other. Now imagine another scenario, guys. Okay, imagine the guy not as attractive. Maybe you think the guy is not very cute. Okay, so look at this guy here. This guy not as attractive. Do you think that there's a high chance that you flirt with this guy? No, right? Okay, there's a lower chance that you will have anything to do with this guy. There's a lower chance of you developing any feelings with this guy. So you compare the anion in this case, is the anion as tempted? No. Okay, it's not. The charge isn't high enough for the anion's electron cloud to be pulled across. So as you can see, guys, there's way less electron sharing in this case compared to this one, where there is a lot more electron sharing. Does that make sense? In other words, to summarize what I just went through, what I just gone through, the factor that we are discussing here is the cation. And when we look at the cation, we are looking at the charge density. Okay, the charge density of the cation, we have learned charge density in the last lesson, right? So the charge density of the cation will actually affect how much covalent properties it has. So let's run through this idea once again. Okay, anyone have any questions first? The more attractive the cation, the more likely you will pull the electron cloud of the anion. I'll still use the word pull for now. Okay, and that's why there's a higher chance of electron sharing. Make sense? So let's look at the explanation now, guys. When the cation has higher charge density, what happens? There will be this thing called higher polarizing power. What does polarize mean? I will just explain it a bit. You can think of it as the ability of the guy to attract a girl or something like that. Okay, so the higher the polarizing power, that means the cation can polarize the electron cloud of the anion to a larger extent. So I'm going to introduce some new words to you guys. What does polarize mean? Polarize means to so-called pull the electron cloud towards itself. Can you see that? Now you look at this guy over here, a completely platonic friendship. This guy, not very attractive. Look at charge, +1. A guy who is not very attractive to you, do you think you want to develop feelings with him? No, right? Okay, so you want to develop feelings for him at all, so that you have nothing to do with him. You're not even tempted. But then as the guy gets more and more attractive, the more you get tempted by the guy, right? So that's the idea. Okay, so here, right, the higher the charge is, the more you will polarize. Can you all see here polarize a bit only? Here polarize more. Polarize means to like so-called pull the electron cloud, to distort the electron cloud. So you learn a new word. You can only polarize electron clouds. Don't tell me polarize anion. It doesn't make sense. Okay, so highlight all the keywords here. And guys, if you can polarize the electron cloud to a larger extent, can I ask you, is there more sharing or less sharing of electrons? Okay, look at the diagram. The more attractive it is, the more sharing there will be, right? So there's a higher degree of electron sharing. And guys, if there's more sharing, that means there's more what? More electron sharing leads to more covalent character because covalent is about sharing. So higher degree of covalent character. So you have to understand, okay, nothing is ever truly 100% ionic. It's always a mix. So the mix is because the cation could be so attractive to the point where you pull the electron cloud towards itself. And that is electron sharing. Can you see that? It's basically forcing this anion to share a bit of electrons with him. Okay? So let's relate this to real compounds, guys. 3 plus and minus KO, please write down AlCl3. 2 plus and minus is MgCl2. Guys, who has more covalent properties? AlCl3, right? Now, let me give you guys a nice way to visualize this. AlCl3 and MgCl2, I like to visualize this in the form of a line. A line which has the same length. Now take a look, guys. Who has more covalent character? Based on your explanation, it is Al, right? AlCl3. AlCl3 has more covalent character, whereas MgCl2 has less covalent character. Now I ask you, if you have more covalent character, that means you have less ionic. If you have less covalent character, it means you are more ionic. And you can see that it's a spectrum. You can think of it as a 100% spectrum. More covalent means you sacrifice some ionic properties. The less covalent you are, that means you have more room for ionic properties. So guys, can you all see AlCl3 is quite covalent, right? His covalent character is so significant, right? That now AlCl3, I need you all to take note, is considered a simple molecular compound. MgCl2 is the covalent character is not that significant, so it still remains as an ionic compound. In secondary school, you all thought it was Al3 plus and Cl minus, right? I mean, yes, because it's metal and non-metal. However, in JC, take note, AlCl3 is now like this. So if you're wondering, if you see your school notes, right, how come AlCl3 is not Al3 plus and Cl minus? Why is it a covalent bond? It's because of its covalent properties. It's high enough for it to be considered a covalent character. Covalent compound, sorry. Why does it have so much covalent properties? It's because Al3 plus, very, very polarizing, very, very attractive. Okay, can? Now, guys, okay, so far, any questions? We've only talked about the cation. We must also talk about the what? The anion now, right? Okay, so the other factor is anion is a lot easier. Okay, so for anion now, guys, you have to look at ionic units. Okay, we are not talking about charge density, guys, because you have to understand. Okay, treat the cation as a guy and the anion as a girl. Okay, the cation, the guy is trying to. Okay, guys, it's always the guy trying to attract the girl, right? Not the other way around, right? Okay, so have you seen the girl trying to attract the guy? Okay, maybe have, but not that much. Okay, so the idea is that here, anion, you don't look at the attractiveness. Okay, so here, anion, you must look at the size. Okay, what does size mean? Okay, so I give you a scenario. The larger the ionic radius, what does this mean now? The larger the ionic radius, the valence electrons are closer or further from the nucleus? Further, right? So if the valence electrons are further from the nucleus, means what? More attracted or less attracted? Less attracted to the nucleus, right? So can I ask you, do you think it will be more easily polarized by the cation or less easily polarized? If it's less attracted to the nucleus, is it going to get easily pulled by the cation or less easily pulled? More easily pulled, right? Okay, so that's why more easily polarized by the cation. Guys, I need you to highlight two things. You only need to tell me this. Okay, I say again, you only need to tell me this and this in your answer. Don't need to tell me the rest. The rest are just for your own understanding. Okay? If you're more easily polarized, that means you have more sharing of electrons or less? More. Higher degree of electron sharing, which leads to what, guys? higher degree of covalent character. There will be questions on the next page which will showcase this. Okay, now we just compare the cation just now, right? Okay, the size of the anion will also affect it. Okay, can? Oh, good. Can, okay, guys. So far, I've gone through one scenario. It started off as platonic, but then they start developing feelings for each other, right? Okay, but then there's another scenario. They started off, okay, it's covalent bonds with ionic character. Now, the reason why I don't have to explain this that much, right? Because it's something we just learned earlier. You will see it a bit. Covalent bonds with ionic character. So it's the opposite. Guys, how to do this one? So y'all can think of it this way. They are a couple, right? Because covalent bonds, fundamentally they are a couple. Okay, and couple is all about sharing, right? But you think about it, do you think you all really share things equally? Like let's say you go out on a date with a guy. Okay, do you think you're gonna split the bill with him? Do you want to? No, right? Okay, you want him to pay more, right? Okay, don't think I don't know. Okay, you all confirm want the guy to pay more. Okay, so it's the same idea. In a relationship, you all don't actually split things equally. Ideally, yes, lah. Okay, but sometimes okay, the guy will pay more, sometimes you'll pay more. I don't know whether that will happen. Okay, but anyways, okay. Take a look. We have covalent bonds, but let me just show you this covalent bond. Is this equal sharing? This particular bond here. Who? Okay, so who here, what do you notice? Why is it not equal in sharing? Because F is more what? More electronegative than carbon. So do you notice this situation here is talking about polar bonds? Maybe the guy pay more is F. You pay less, you are carbon. That's the idea. Yeah, that's what I usually do also. A bit hiring. Okay. But anyways, yeah, okay, so that's the idea here. We are going to go through this because it's literally just electronegativity difference. There's nothing explanation for, there's no explanation for this. Okay, we already explained this now. And also it can go both ways. Okay, couples, they don't share things equally. Or this one, they start off as friends, but then they start developing feelings for each other. Okay, so it all ties in together. Any issues here? Cannot. Okay, we don't have time to do the questions. So what I want you to do is write the explanation yourself. Now let me tell you something. This one, right, once you understand, it's 3 marks in the exam. Because if you look at the questions, right, they can only ask one thing. What's the degree of covalent character? Then the explanation is just this or this. No application necessary. And this is amazing. If there's no application, you just need to study and you just need to plan your explanation into the question. Okay, so let me break down the question now because there's a bit of a different phrasing that they use. And then afterwards, you all can go back and try this yourself. Explanation is already what I already gone through here. So guys, look at, just read the question now. They say something about MgCl2 deviates more from the A, they say ionic model. And if you look at B, right, it says it deviates more from the theoretical lattice. Honestly, they're just trying to make your life difficult because the question is really so easy itself, right? So they try to change the phrasing to make it harder for you guys. But honestly, look past it. Okay, look past it. What does ionic model mean? Okay, let me just tell you all. Ionic model literally means 100% ionic. Is anything really 100% ionic? No, right? Okay, so guys, if you deviate more from the ionic model, that means you're more what? Covalent. Simple, right? Yeah, okay? So guys, what's theoretical lattice energy? Can you all recap? Can you all remember from the last lesson what on earth is lattice energy? It measures what? It's a direct measure of strength of an ionic bond. Okay, so lattice energy is to measure ionic bond strength, right? So it's the same idea, law. Guys, theoretical means what? Now, you know that in theory, theoretical, right? You want it to be perfect, right? In theory, ideally, right? Okay, so theoretical literally means 100%. So theoretical lattice energy means 100% ionic. Same shit, they just change the phrasing only. Honestly, nothing. Okay, so now you understand what this means, right? Go do the question. I'm pretty sure y'all can figure out what factor to use. And whatever factor, right, just follow the phrasing, that's your answer already. So it's honestly not difficult. Just go and copy this yourself. Okay, Ken? So again, let's look at what we did today. Okay, main thing is VSEPR theory. Shape and bond angle, that one we will go through more in the tutorial and the revision lesson. Yeah, after the tutorial lesson, right? Okay, I will have one revision lesson for chem bonding as well. Because that's how important this topic is. Okay, next, electronegativity, we learn polar and non-polar molecules. Remember, next lesson we need to know what is a polar, what's a non-polar molecule. So just remember that before next Monday, is it? Yeah. Okay, and then finally, we have the last thing. What's the last thing? Okay, this intermediate bonds, very, very short. Okay. And yeah, if you have no more questions, that's it for today. If you have anything to ask from the school or whatever, you can still ask me. I'll still be here. No more class really. Okay, good.